Hello, everybody. Guess I'm supposed to start now. So my talk's going to be on Global Mutable Secondary Indexes in Phoenix. And I'm a software engineer at Salesforce. So quick overview of what I'll be talking about. So start with the intro to secondary indexes. And then we'll talk about some of the problems we've run into at Salesforce when we ran secondary indexes at scale. And then I'll talk about some new tooling that we've developed in the recent past to sort of help with secondary indexes. And then we'll talk about the future direction of secondary indexes. So I think for a lot of people in this room, this is probably like a remedial slide. What is a secondary index? So this is just a quick example of why we need secondary indexes. So I have a table here, an HBase table, customer table basically. So if I look up based on the row key in HBase, that's very fast, right? So I have these two explain plans down here. So on the left, I'm kind of selecting by order ID, which is the row key. So that's a point lookup, so that's very fast. On the right side, I'm querying by another column. And that's essentially a full scan. So essentially what you're doing is you're just scanning the whole table, filtering by customer ID. And so that's going to be really slow, obviously, right? Especially if you have a big table. So here I've created an index on my table. I'm now indexing on customer ID. And so now with this index table, if I do an explain on the query with the customer ID, you see in the query plan now the full scan has turned into a range scan, which is a lot faster than a full scan. So that's what a secondary index is. What's a global secondary index, just so we kind of know what we're talking about here. So I'm going to differentiate between local indexes and global indexes. So local indexes, the index is stored on the same region, or same table and same region essentially as the data table. So it's essentially what we call a shadow column family on the data table. And if you have HBase 1.3 or higher, it's actually an atomic write. So you write to the data table and the index table at the same time. When you read, however, you need to sort of ping every region holding, well, basically every data table region. You need to ping every data table region when you do a read. And we could talk about why later on, but that's one of the drawbacks of local indexes. For global indexes, your index table is separate from your data table. And so what that means in HBase is, your index table regions could be on different region servers from your data table regions. What it also means is when you do a data table write, you're going to do potentially a cross-server RPC call to write to the index table. So in this example, right, if I'm writing to region server 1, the data table on the back end, it's going to do a server-to-server RPC to region server 2 to write to the index table. So the consequences of all this is that for local indexes, they tend to be better for write-heavy use cases because obviously, you don't have that overhead of the RPC that you do in global indexes, but you do have that read time hit that I talked about. Whereas for global indexes, they tend to be better for read-heavy use cases. You do have that RPC overhead when you're doing a write, but when you're reading, it's basically like reading from any other HBase table. You look up in meta, and you go straight to the region server that you need. This pretty much is just what I just said. Yeah, I already kind of just covered all this. Another thing I should mention at the bottom, Phoenix 3941. So for local indexes, we've actually done a sort of optimization that kind of mitigates that drawback that I just mentioned about having to ping every region server, every data table region server. You can actually prune which region servers you need to hit based on a common prefix between the data and index tables. So a good example of that is if you have a multi-tenant table, you can sort of prune based on tenant ID. So that's what a global secondary index is. What's a global mutable secondary index is. So now it's sort of distinguished between mutable and immutable indexes. So immutable tables, obviously, once you've written to them, you can't update any rows in there. The index maintenance is done entirely on the client side, so it's up to the client to basically write to both the data table and the index table. For mutable tables, you can update the data, and the index maintenance is done on the server side via that server-to-server RPC I sort of talked about in the last slide. The problem with that is, sometimes your index can get out of sync, and we'll get into sort of reasons how that could happen. So I guess there might be a question, why can immutable index maintenance be done on the client, but for mutable index maintenance, why do we have to do it on the server? Well, the reason is because for mutable indexes, when you update the indexed column, you need the previous row state in order to properly update the index table. So I'll show you an example here. So, I have a data table. Let's say I insert some row like with order ID 01 and customer ID C21, right? Pretty straightforward. And if I update that row, let's say I update the customer ID now to C55. I need to generate sort of two mutations here, right? I need to do a delete on the prior index table row, and then I need to put the new index row, right? And in order to generate that delete for that prior index row, obviously I need that prior row state, because that's how I know the C21, right? So that's kind of why you need to do the index maintenance on the server side. So global mutable secondary indexes, yeah, this is what the talk is going to be about. Index tables in a separate table, better performance for read-heavy use cases, and index maintenance is done via that server-to-server RPC. And the index can potentially get out of sync, unlike local indexes. So one other distinction, I probably should have titled this talk actually non-transactional Phoenix Global Mutable Secondary Indexes, but so just really quickly, transactional versus non-transactional. Transactional, essentially, you're going to have a transaction manager that can help you with all this, and so where you can have where you have basically all your mutations are ordered by transaction ID, and then you can have rollbacks and things like that. But I'm only going to be talking about non-transactional indexes, and actually in the last part, in the future direction, we'll take a little bit of a look at transactional indexes. So an anatomy of an index write, this is what an index write looks like. So just a quick example of a Phoenix client. I write to a region server, which is holding my data table. That gets picked up by a handler pool, which processes my mutation to the data table. And so in HBase, when you're doing a mutate, you have these coprocessor hooks. And so Phoenix is nothing more than a coprocessor, right? And so we have a Phoenix indexer coprocessor, and we sort of hook into that mutate, and in the pre-batch mutate call, we sort of build the index update. So we haven't written the index update yet, but we just sort of generated it and sort of know what mutation we need to do. And then later on, after the data table row has been written, in post-batch mutate, we actually write the index update. So that's when you do that server-to-server RPC. So step 5 here, in this case, my index table happens to be on another region server. I do that cross-region server RPC, and then I mutate the index table that way. So question, why do we build the index updates before writing them? Like, why have separate steps 3 and 4 here? Why not just do it together? Well, the reason why is because there's actually a step 3.5 in between where in HBase we're doing the wall sync. So we're in the write-ahead log, we're writing the index update alongside the data table update. And the reason we do that is because if the server crashes before we get to step 4, right, we want to make sure that index write happens. So during wall replay, like the normal HBase wall replay when your region server crashes, as you replay the wall writes, you'll also do the index updates at the same time. So failure handling, what happens if that server-to-server index write fails? That means your index table is out of sync, right? Because we've written to the data table potentially already, and we haven't written to the index table. So the way we handle this in Phoenix is every index has a state, and normally the state is active, but when we have an index write failure on the server side, we sort of detect that and we mark the index as disabled. When the index is disabled, we no longer use the index. So index maintenance isn't happening and your queries are not using the index. We have a rebuilder thread that runs on the system catalog region server that basically pulls for these disabled indexes. And it basically then transitions the state to inactive. And then when you're in an inactive state, index maintenance proceeds. And then what you do is you sort of backfill that time between the time your index got disabled and the time it became inactive. And that's what the rebuilder does. It basically replays those mutations in that time period. And then it marks the index back to active. So a quick example of how that happens. So again, the rebuilder thread runs on the system catalog region. We have a region observer called metadata region observer. It issues a special scan against all the region servers holding data table regions. And it puts a special attribute rebuild. And on those data table region servers, we have an observer that basically intercepts that and reads that attribute and knows, okay, this is a rebuild scan, and then it kicks off a rebuild on its local data table region. So now let's start talking about some of the problems we ran into with secondary indexes. So I have this slide called dining index writers because some of you might be familiar with the famous computer science problem, the dining philosophers problem, where you have a bunch of philosophers sitting around a dining table. There's forks in between each of them, and each philosopher needs 2 forks to eat. And if every philosopher follows the policy of reaching for the right-hand fork first, then you get into a deadlock, right? And nobody can eat. So with secondary indexes, we can potentially get into something kind of similar. So in this example, I have a Phoenix client that's writing to my data table, right? Region server 1 picks up the 2 concurrent requests to write to the data table region. Now in this example, I've sort of laid it out such that if you notice on the left-hand side, the data table region, the keys that it's responsible, the key range, OA to OB, the index table that matches that sort of data table region, it happens to be on the other region server, right? So in this case, when I'm writing customer C55, C56, I need to write to the index table region that's responsible for that key range, C50 to C60, right? And so that's why it's going to region server 2. So similarly, if I have a client writing on region server 2, it has a data table region, and the index table region that it needs to write to is on region server 1. And so in this example, it's sort of a contrived example, right, where I have only 2 handlers. And now, because my Phoenix client has used both of my handlers, I'm kind of in a deadlock, right, because I don't have any available handlers to handle the server-to-server RPC writes that I need to do. So how do we sort of resolve this? So in Phoenix, we have this thing called the Phoenix RPC Scheduler Factory. This is something that you configure in your HBase configuration with this XML here. And basically what it does is injects a custom RPC controller and a custom sort of handler pool in HBase. So what the handler pool does is gives you a special handler pool that only handles index RPC requests. And what the RPC controller does is on your outbound index writes, it marks them as index priority. So that's how sort of HBase knows to use the index handler pool. So this is what it looks like. Now I have this extra handler pool on each region server. So and those don't handle client requests, right? So this kind of helps resolve that deadlock that I got into. So the problem with this is kind of hacky. So the way it really works is we can't really tag only index rights. We basically, what ends up happening is you tag all non-system table RPCs. What that means is basically every table besides system catalog gets tagged with this index priority. And so that creates some problems potentially. If you're doing index rebuilds, in that earlier slide I had the index rebuild scans, those would be using the index handlers. And then when those do the index writes, their index writes would also be using index handlers, so you could potentially have that deadlock again. So one of the future things we want to do is HBase 1.4 is a new feature that lets the client set the priority on every operation. So then we wouldn't need to inject all this custom stuff. We could just set it from the client directly, like this is the index priority for index writes. So some issues that we saw in production. So we had a case where we had a cluster basically locked up. We looked at it, all the region server handlers were tied up. And what had happened was a region server holding an index region. So we had a region server that was running an outdated version of Phoenix. And that caused the server-to-server index write to fail. And remember, when an index write fails, the index gets disabled. And so so the index got disabled, and that kicked off the rebuild from the rebuild thread, right? But when we looked at it, all the rebuild threads were tied up. And so when all your handlers are tied up, so the example I gave earlier, that was very contrived. You only had 2 handlers on each region server. They were updating exactly a certain way. So it was very contrived, but when all your handlers are tied up, then it becomes kind of a real problem. So what we found is, why was the rebuild getting stuck? It turned out that there was this bug where they were getting stuck in, there was like a sort bug essentially. And if you had rows with a large number of versions, it would be really slow. So we had, I think, rows with a few hundred versions for each row. And so we were really stuck in this. So we had a fix for that. So this is sort of just a visual representation of the problem that I just described. So, so say your index is disabled, and say you have this bug that's causing your handler to get stuck in sorting, right? So your index is disabled, you're kicking off a rebuild, the rebuild is stuck on the sorting. So what happens is the rebuilder thread the scan is going to time out. So scan 1 is going to time out, and it's going to try to reissue a new scan on another handler. But meanwhile, handler 1 is still tied up because it's stuck in that sort. And so what happens is you just keep repeating this, right? Like if you're stuck in a sort for a really long time, you're just going to keep this, and you're just going to eventually run out of handlers. So the fix we had for this was, in addition to the sort, obviously you fix the sorting problem first, but then also to prevent this, we have the rebuild scan. We increase the timeout, and we only try once. Similar thing can happen for just regular index maintenance. So an example of this that we ran into is, say you have an index region that's stuck in transition. So in this case, in this example, you see the Phoenix client trying to do a data table update. We have that server-to-server RPC, but that RPC is stuck because there's an index region stuck in transition. So again, same thing as the slide before, like your client is going to retry, but your handlers are going to get stuck in that long timeout. And so you run out of handlers. But this time, actually, you're running out of handlers on region server 1 because it's actually the client handler pool that's getting tied up in this. So that's pretty bad. So one of the ways we tried to mitigate this when we first saw this problem is we tried to shorten the time out for that server-to-server index write. The problem with this is it's tricky to get the timeouts right because you have to sort of adjust both your client side timeout and your server side for that server-to-server RPC. That timeout is a separate property, right? Because that's on the server side. So you have to adjust both your server and client side to sort of handle this. And you want it, so basically, if you look at this slide, the RPC timeout here it should be less than whatever your client timeout is, because it doesn't make sense if it's longer, right? Because if it's longer, then it's going to be stuck there while the client retries. So it should be, so your RPC timeout should always be shorter than your client timeout, but yet you want your client timeout to be long enough to write out common scenarios like region splits, region moves, so on. A better solution that's in a newer version of Phoenix 4.14 that just came out, Phoenix 4130. So what we do here is we don't even retry the server-to-server index writes. Instead, we just try once, and we let the client retry its write. And so, so what happens is if the client does a mutation and the index write fails, on the server side, instead of marking the index as disabled, we mark it as pending disable. Now there's now the client's going to retry, and there's two potential outcomes, right? Either the client retries and it succeeds, then we transition the index back to active. But if the client retries and the retries are exhausted, then we have to mark the index disabled and attempt a rebuild. So another reason why we have this pending disable state is if for some reason the client goes away, the client dies, the rebuilder thread will detect that it's been in pending disabled for too long, and it'll transition it to disable. This makes it simpler, so now we don't have that separate client-side and server-side timeout to adjust. We only have one knob to turn here, and now we can be sure that every client mutation is only using one handler. So for index updates, the timing of your index writes is kind of tricky. So HBase has this series of steps that happen when you're doing a mutation. So you acquire your row locks, you call your coprocessor pre-batch mutate hook, you write to the write-ahead log in memstore, then you release the row locks, then you sync your write-ahead log, and then you call your coprocessor post-batch mutate, and then you advance to MVCC. So remember in the earlier slide I showed that in the pre-batch mutate we sort of generate the index update. Now when we do that, it's important that we have an exclusive write lock. And what we found was that HBase 1.2 and higher, you actually don't have an exclusive write lock here. So HBase 1.2 and higher, they allow concurrent writes. So that's a problem for Phoenix indexes, right? So what we do is actually we do the row locking in Phoenix itself. So with this Phoenix 4053, we actually lock the row in pre-batch mutate, and I believe we release the lock in post-batch mutate. So that was one problem. Another problem is we were doing the index write in this post-batch mutate hook, right? And so if you look at it, it comes before you advance the MVCC. And I won't go into, I don't have time to go into like how MVCC works. It's, how HBase does, it's multi-version concurrency control. But basically all you need to know is that in order to complete your write, you need to wait for all previous writers to sort of advance the MVCC. And so this is very bad for pretty obvious reasons, right? Because if I'm stuck in post-batch mutate, let's say I'm stuck in a long timeout for that server-to-server RPC write, then I'm not advancing my MVCC, then that means in HBase all my writers are stuck sort of waiting. So that's very bad. So what we did is in Phoenix 3789, we moved the index write to post-batch mutate indispensably is what they call it. So it's just a way, I guess, to differentiate. So it now comes after the MVCC, so you don't have that problem. But there is a consequence of this. So for those of you that know MVCC, you know that when you increment the MVCC, that's when your write actually becomes visible, right? And so this obviously changes the semantics a little bit. So before, our index writes were visible just before the data table write became visible, because we were writing in step 6. But now, since we're writing in step 8, our data table write becomes visible before our index table write. Now, obviously, the gap between all these should, in theory, be pretty small, because but there is a gap, and this is the problem with non-transactional indexes. Is you're always going to have this small gap, and we sort of changed where that gap is here. So new tooling that we've developed for secondary indexes, we now have an index scrutiny tool. So how do you know whether your index table is in sync with your data table? Well, you need basically to, well, what we found is we needed to write this tool, and this tool basically is a map reduce job. And it scans, so map reduce job, there's a mapper for every data table region. And so each mapper will sort of iterate over the rows that it's responsible for, and then check in the corresponding, check if the index row exists. Now you might want to reverse that, so you might want to scan over your index table and check if your data table rows are there. And the reason why you want to do that is because, in this example, I have two orphaned rows, right? I have a data table row without a corresponding index row, and I have an index row without a corresponding data table row. Well, in order to find both of those rows, I need to do separate sort of map reduce jobs, right? First, I need to scan over my data table, then check against the index table. And then to find the index table orphan row, I need to scan over my index table and do the opposite, right? Check if the data table row is there. So when your data table is very large, what we found is it could be tricky to build an index after you already have a lot of data. So say we have this huge table. Now, if I just go to SQL line, let's say, and I say create index on this huge table, it's going to be synchronous by default. So what it does is does an upsert select to select from your data table and upsert into your index table. This is supposed to be a server-side thing, but because there's a bug here where our priorities are not right and we have that sort of deadlock scenario that I mentioned earlier, we've actually disabled server-side upsert select for this. And so it's client-side, and that's pretty bad because basically what that means is your client has to, it has to, basically your region servers have to send all the rows back to your client, and the client has to process them and do the index mutations, which is not feasible for big tables, right? So then that's why Phoenix has this build async. So if you build asynchronously, it's actually a map reduce job. So we have this Phoenix MR job submitter that we run as a cron job that checks for indexes in building state. So your index gets marked as building when you run this command. And so the Phoenix MR job submitter create a map reduce job, and you have a mapper for each data table region. So that's more scalable, obviously. But then you run into this problem. So say I have thousands of region servers potentially, right? When I first create my index table, I only have, in HBase, unless I pre-split, I only have one index region. And so that region is going to get crushed by all these writes. And remember, when we have failed index writes, we disable index. So when we're doing this, these mappers that are doing this rebuild, they're just using the normal Phoenix client. So they're doing the same normal stuff where, if the index write fails, it disables the index. So how do we resolve this? Well, ideally what you want to do is you pre-split the index table. That's kind of obvious, but what's harder is how do you split the index table? So how do we know basically what keys to split on essentially? Because you don't really know your index column values ahead of time, right? So what we need actually is something like this. So an equidepth histogram is a histogram where all your buckets have the same frequency. And in this case, what we want is we want to split our index table such that each region has the same number of rows. And so imagine this was the key ranges for my index table. Well, I need to find these key ranges in order to pre-split my index table properly. So how do you do that? So we wrote this Phoenix 4724. It's basically, it is that equidepth histogram. It's all you need to know is it's pretty efficient. The way it works is you're kind of actually simulating what HBase does, because what it does is in the histogram bars, as you keep adding values to a bar, it splits. And then if you have too many bars, then it starts merging the smaller ones. which if you think about it is basically like HBase region management, right? Like you're splitting large regions, you're merging small ones. This is very efficient, logarithmic space, which is good. And then we use this in Phoenix 4704. So we added a feature to the index tool, which is the thing that basically creates the MapReduce job to rebuild your index. And we use a table sample feature, which is also a relatively new feature. So table sample lets you do a Bernoulli sampling of your data table. So Bernoulli sampling, that's just, it means every point has an equal chance of getting selected. And so it's a fair sort of selection. And then, so then now we have these histogram bounds, and then we pre-split our index table based on those bounds. These are in 4.14, yes. Yeah. So quick talk about some future stuff. So key takeaways so far of this talk is, that server-to-server RPC, that's what really kills us with secondary indexes, right? It can be cumbersome. We get into those deadlock scenarios because when we have a bug that for whatever reason ties up a handler, then you start getting into these deadlock-like scenarios. And they're difficult to keep consistent. So remember I showed the steps in HBase where the MVCC happens. That means you're always going to have that small window where either data write's visible first or your index write's visible first. It's not atomic, whereas local indexes, as I mentioned earlier, they are atomic. So that causes some issues also because we found a lot of subtle bugs that can get your index out of sync. For example, I'll just briefly mention one bug we found is, in HBase, the order of your client writes aren't guaranteed, and so potentially you could have, a write for the same row, a write in the past come before the write in the future, and so that you never really get your mutations. You're not guaranteed that your mutations are going to come in order, and so that was very difficult to handle. That caused the index to get out of sync. So all these kind of subtle bugs that makes it so we need all this additional tooling, right, which is kind of operational overhead. And then if you think about it just in terms of the CAP theorem, right, like what we're trying to do is we're trying to cheat the CAP theorem essentially, right? Basically, we want both consistency and availability. So we want the index to be as consistent as possible. That's why we sort of do the server-to-server RPC before we return back to the client, so that by the time we return back to the client, both the data and index table writes have happened, so it looks consistent. And that's why we have to manage the ordering with the MVCC and everything. And then we also want it to be highly available, right? And so that's why we need the rebuilder thread, and we have all these state transitions and all of that. So it's difficult, basically, is what I'm saying, to have both a consistent and available index. And so what are some possible solutions to this? So local indexes is one good possibility. So it looks really attractive because the index update is atomic, right? And since it's atomic, you're sort of guaranteed that you won't have any out of sync issues. You either write your data table and index table write together, or you don't. So my coworker actually did some performance testing on local indexes. What we found, it's a pretty small cluster, only 4 nodes, but what we found was that for writes, it was a lot faster, 3x faster for upserts on local indexes versus global indexes. And then in terms of network utilization, you have 5x less network utilization because you don't have that server-to-server RPC that's happening on your network. So for reads, we actually found it was similar performance, but there's a big caveat here is that, remember, the nodes, we only had like a 4-node cluster, so this is not really truly representative, I would say, of a large cluster, so we need to do further testing on that. And in theory, because for local indexes, you have to do that ping on every data table region, as you increase the number of regions you have, you're likely to get a performance hit. And your availability will also likely suffer, right? Because that means every data table region has to be available to be able to read. And that kind of sounds scary. So for non-covered local indexes, we found that there's a performance penalty as the number of rows that match your query increase. And we still need to figure out why, but that's some oddity that we found. Transactional secondary indexes. So this is also an attractive potential future direction. So now you have a separate transaction manager. And what that allows you to do is you basically have atomic index rights, right? Where your index table and your data table are still separate, but you can still have your updates be atomic. The problem with this is your data table and your index table both have to be available in order to complete your data table right. So your availability is going to suffer a little bit because of this. Whereas before, if you think about non-transactional indexes, we kind of compromised on the consistency a little bit, because if the index write fails, we just disable the index for a period of time, and then we hope that we can sort of rebuild it from there. And so that makes it so you can still write to your data table. So it's a little bit more highly available. But this gives you basically stronger consistency and at the trade-off of lower availability. And so there's a relevant PhoenixCon talk that I highly suggest you guys check out. There's a talk on one of the transaction managers, OMID. And that's pretty much it. And now I'll take any questions. Sure.
When doing local index reads, are the reads to all the reads from parallel?
So the question was, when doing local index reads, are those reads done in parallel? Yes, they are. Yeah, so there are some things that you can tune here. The question is, can we compromise, for example, on consistency a little bit? Because what they were finding was that they were doing a lot of index rebuilds because their indexes are getting disabled very frequently. And so the answer to that is yes, you can. So there's actually some configuration settings. So here, when I said the index gets marked as disabled, that's actually configurable. You don't have to mark your index as disabled. You can just keep your index active. If you're OK with like missing some index updates and having a little bit of consistency problems there, like you can actually just, OK, don't do anything if your index write fails. Just keep your index active. You're still serving queries from your index, but you're missing some index rows potentially, which some use cases can sort of live with. And so that's configurable, actually. The other thing you can configure is whether to stop index maintenance when an index gets disabled. That's also something you can tune. So those are some things that you might want to look into.
That's configurable. So few of the indexes can be, we can configure in a way that it's not being disabled and the handlers are not being stuck.
So the question is, how configurable is this, I guess? That's right. So basically, you're right. The handlers will not get stuck because essentially, well, here you're basically step 5. You're not retrying that, and so you're right. Yeah, if you're not retrying 5, then you're not really. You lower the possibility of your handlers getting stuck. Okay, that's it. Thank you.